Welcome to qnawire.
Welcome once again to a new problem. This time we have a power output. So we have a power output of 10 to 25 watts, and this is connected to the power of the wings of of birds that are flying. So this is a bird. This is a bird flying. And so what they're saying is that on average, the power output for the wings for all birds happens to be 10 to 25 watts per kilogram. That's the power output, and it's independent of the size. There's a specific type of bird called Indian giant hummingbird. It's a hummingbird and has a scientific name. I think it's called Patagonia um, gigas. That's just the scientific name of the bird. It happens to have a mass of 70 grams. Easily, you can transform that to kilograms. So 1 kilogram is 1,000 grams. If you multiply that, you get these two zeros cancel out. So you have 0.07 kilograms. That's the mass of the bird. The other piece of information that we're given is that it flaps its wings 10 times per second. So it flaps its wings 10 times per second, and that allows it to to go up, to fly up. It goes up by flapping its wings 10 times per second. So the question is, how much work is done each time it flaps its wing, which we call the wing beat. Okay, that's the wing beat. So the 10 to 25 watts, that's the range for all the birds. But then if the bird weighs 0.07 kilograms, we can say that its range is going to be 10 joules, or rather, its range is going to be, I need to simplify that. Its range is going to be 10 watts. So it's going to be 10 watts times 0.07. So that's a fraction based on the weight. 225 watts times 0.07. So what's happening here is, remember, we have an Indian giant hummingbird, and a typical bird, any kind of bird, has a wing power of 10 to 25 watts. So if you bring in the weight, we can get the fraction of the power based on the size of the bird. We can change this to, this becomes 0.7 watts all the way up until 1.75 watts. Okay. So if we want to find out the 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 power in one wing flap or wing beat, we'll say, or the work done in one wing beat. Remember, work is power times time. But then this time we don't have any time. We have wing beats, so we have to do some kind of transformation. If we have 10 wing beats per second, so 10 wing beats per second. That's what we're given. And if we take the power in terms of joules, we're going to have 0.7 joules per second. That's the total power it's flapping, and then we divide by the number of wing beats, 10 wing beats per second, and that gives us 0.07 joules per second. or rather 0.07. We have to rectify that, not joules per second, but joules per beat. The seconds cancel out. So this second right here, and that second, they cancel out. So we're left with 0.07 joules per beat. So that's for this range. For the second range, which is 1.75, the work done by the wing beat becomes 1.75 joules per second divided by 10 wing beats per second, and that gives us a different range, which is 0.175 joules per beat. So you can see in the next page that if we have the Indian giant hummingbird and it weighs 70 grams and flaps its wings 10 times per second, then each flap or each wing beat will range from 0, 0. 0. Gotta do that, 0.07 joules per beat, all the way up until 0.175 joules per beat. That's what we have. The second part of the problem is a different assumption. So you're assuming if you had a human being, for example, and they had wings, okay, they had wings, and the steady power for their wings happens to be 500 watts. But if they're flying for a few seconds, the what we can call few seconds power is 1.4 kilowatts. If you change that to watts, you get 1,000 watts per kilowatt, and so that's 1,400 watts. That's the scenario we have. We want to get the power output per kilogram. If the size of the human being, it's like an average human being, an athlete. This is an athlete that has a mass of 70 kilograms. So if the power happens to be 500 watts, the steady power, and they weigh 70 kilograms, it means that for each kilogram, they're expending 7 watts per kilogram. 7 watts per kilogram, unfortunately, falls outside of the range of 10 to 25 watts that allows birds to fly. So it means that at steady state, an athlete cannot fly. If we change it a little bit and say, okay, how about if they're expending 1,400 watts? So 1,400 watts divided by 70 kilograms, we end up getting 20 watts per kilogram. That looks good because it's in between this range, but the problem is that it happens only for a few seconds. So this is the power for a few seconds. So that's the problem we have. So once again, looking at this problem, we had the Indian hummingbird, and it weighs 70 grams, and it's flapping its wings 10 times per second. We want to find how much work is done in each beat, each wing beat, each flap, and so we have to take the power, the total power, this one right here. We take the two different ranges, the 10 watts and the 25 watts. We change that to relative power by multiplying by the weight of the bird, which is 0.07 kilograms. And we get a range of 0.7 joules and also 0.7 joules per second and 1.75 joules per second. And that helps us compute the beats. So if we divide that by 10 wing beats per second, we get the first range, which is 0.07 joules per second, and the second range is 0.17 5 joules per beat. So joules per beat, that's the range they get for the wing beat. In the second part of the problem, we do for an athlete who weighs 70 kilograms with a power steady output of 500 watts. And so if you divide by 70, this is how much they expend per kilogram. Unfortunately, this is super low for them to fly. For a few seconds, they can have a power of 1400, but that's just for a few seconds, and it gives them 20, 20 watts per kilogram. I need to change this right here. So this is watts per kilogram. This is 20 watts per kilogram. The problem with that is that it only happens for a short time. The 20 watts per kilogram happens for a short time, so they can't sustain themselves flying in that period of time. I hope you enjoyed the problem. Feel free to send me any questions, and hope to see you next time in the other problems that we're going to be working on. Okay, thanks. Bye.